So good afternoon, everybody. So let's start the afternoon session. So the first speaker is Tadashi Takayanagi. He is going to tell us about quantum entanglement and holography.
Thank you. First, I'd like to thank organizers for inviting me to this very wonderful winter school, and especially Sandeep. And in these three lectures, I'd like to discuss about the recent developments of quantum entanglement and holography, and especially from the viewpoint of the quantity so-called quantum entanglement entropy. So my lecture plan is as follows. So we start with some detailed introduction why we consider this quantum entanglement or entanglement entropy and so on, and what is the definition of that. And also then we go to the practical calculation of this quantity. And just EE means entanglement entropy in quantum field theories. And then we move, this is in quantum field theory, and then we move on to the calculation in the ADS-CFT correspondence, which is called holographic entanglement entropy. And then later we are discussing about the latest developments and from the viewpoint of two different aspects. First one is a so-called the entanglement renormalization and its relation to holography. There is a quite interesting real space renormalization group description of some quantum state. And recently it has been very pointed out this entanglement renormalization is closely related to just ADS-CFT. And this quite interesting subject. I'd like to give some review of that, and including our recent results. And finally, also I'd like to discuss the another development, which is the excited state. So we compute entanglement entropy for excited state and how it behaves and what is the time evolution of that. We'd like to discuss, including our latest works. And so I just give some few references and about review articles of this, for example, entanglement entropy in quantum field theory or quantum minimal systems. We can, for example, look at these articles. And there are also something other review, nice review articles, but I just give a few of them, and also holographic entanglement entropy and relation between entanglement entropy and black hole entropies. Now, we're not going so much detail about this kind of topics. Okay, so let me begin with the introduction. So first, I should explain, this is some school, so I should explain what is the entanglement and what is the entanglement entropy. So first of all, we should ask what is a quantum entanglement. This is a quite basic property of quantum mechanics. In quantum mechanics, a physical state is described by a vector, some state in Hilbert space, as we know. And if we, particularly if we consider the simplest example of spin system, just one spin, if we take one spin of electrons, which is just Hilbert space is now just two-dimensional, an up spin and down spin, and it's a state. Any state is just linear combination of these two states. So this is orthogonal basis, and we can just normalize. We defining norm, we can define to be just norm is 1. So then we have linear combination, and this we normalize this state psi, then we just have this constraint. But there are, so this kind of continuously many configurations are allowed as a ground, some state, a quantum state of the spin systems, just one spin system. And if we consider some slightly more complicated system, which is just two spins, we can consider two electrons, and two electrons have some independent spins. And in that case, we can think about really quite a lot of states, but just to pick up two extreme limits of such states. So first example is this direct product state. So this is just direct product. A and B is just the position of spins. We have some spin. The electron, first one is called A, and the other one is B. So A spin is up and down. It's mixed. It's a linear combination, but just direct product of second spin. In this case, even though there are some complicated linear combination, but they are actually independent. So if we measure the A spin, this spin of A, first spin is up, but this measurement doesn't affect the measurement of the spin B. So if we assume this, then this is the direct product. So they are independent. So in that case, we call this state as unentangled. Entangled means there is correlation between them, so it's not an entangled state. But in the opposite one is a really entangled state, and indeed this is a maximally entangled state, so-called EPR state. So this is actually singlet. For example, one example is singlet state, like this, up spin and down spin, and down spin and up spin. In this case, there are very strong correlation between A and B, because if we measure the first spin is up, it's always second spin is down, and the opposite also true. in that sense, one determines the other. It's a very strong correlation. And if we can also imagine this A and B is really spatially separated for a long distance, but still this kind of correlation remains. So this kind of quantum entanglement gives quite non-local correlation, but which doesn't any conflict with any basic principle of physics. There are no contradiction, but just this gives very deep fact of this quantum systems. So, but this is quite interesting behavior, which only happens for quantum mechanics, not happens in a classical mechanics. So this kind of behavior is, we define it in a very abstract way, but it is good to measure it in some by looking at some particular quantity to as a some real number or something like that. So this nice measure is actually one of the best measure. There are also other measure, but one of the most important measure is so-called entanglement entropy, which we will define below. We just this is a long word, so I just call it EE. And this is a very simple way to define this. And so we just have some Hilbert, total Hilbert space, H tot, this total Hilbert space. You can imagine a lot of spins, for example, or a previous just two spin examples. Then we just decompose this total Hilbert space into two pieces, A and B, just factorize. Direct product of HA and HB is equal to this total Hilbert space. So in a spin chain example, you can just artificially cut it at some point. Just call this part is A and the other part is B. But there are infinitely many different ways to define this if we have infinitely many degree of freedom. And then we just, what we do is just to forget about the other part B. We just trace out this B, Hilbert space HB. So we have rho tot is a reduced, rho tot is a density matrix, total density matrix of the original system. And we trace out this subsystem B, so this HB. We trace out B and define some coarse-grained density matrix, so-called reduced density matrix, rho A. And for example, in a zero temperature and some pure state, we can have some wave function psi. It's a total density matrix just given by this. This is a completely pure state, but after tracing out this B, region B, subsystem B, we have some, in general, we have some mixed state result. And then finally, we define this entanglement entropy. So somehow, sorry, this is some problem about this type of sum. So I just write it here. We just using this reduced density matrix, we define entanglement entropy by entropy. So rho A log rho. So rho log rho is minus sign because rho is a density probability it's less than 1. So that means it's negative. So we put minus sign to get. This is a von Neumann entropy, and this is the definition of entanglement entropy. So I just come back. So then I come back to previous simplest example of two spin systems. So first one is this direct product state. We can define some reduced density matrix rho A by tracing out this B, this Hilbert space B. So then we immediately find that this matrix looks like this. This is mixed, but actually we can diagonalize it. It's just 1, 0. Its eigenvalue is just 1, 0. And this is because just B, A and B is really independent. Just we have this one state, and this one state corresponds just 1 here. And in this it is clear that this, if we trace sum over two components, this is 0 or this is 0, so that means entropy is 0. So there are no entanglement between them as we expected. So if we measure the first spin is up, but still we cannot tell anything about second spin, it's totally independent. And on the other hand, if we look at this kind of thing, we should put minus sign to have a singlet, but also even if we put plus sign, the entanglement nature is same. This is also maximally entangled state. And if we have this kind of state, so we can trace out this subsystem B. There are two possibilities, and accordingly, we have some two states, two diagonal components of this reduced density matrix, 1/2, because we normalize this trace of rho A is always 1. So it's a 1/2, and that means it contributes 1/2, and it's minus 2 times 2 log 1/2, it's like log 2. So this 2 exactly means that there are 2 degrees of freedom, 1 and 2, and they are really entangled with each other. So in this case, if we measure the first spins up, then immediately know second spins down because of this state, and vice versa. And in that way, they are strongly, we call it very strongly entangled.
You're saying it's instead of 2 log half, it should be just log half, or 2 into 1 over 2.
Sorry, you're right, you're right. So I just, sorry, I didn't write it. One half, sorry, one half is missing. You're right. Sorry. Exactly. Sorry, this is my part. So, but just in case those who are not so much familiar with density matrix formalism, I just quickly mention that. So we have some pure state, and pure state is defined by just standard wave function. So this is a standard way to describe quantum mechanics. And if you have wave function, we can define this matrix, Bra and Ket, it's combined this way. And in this formalism, a density matrix formalism, this is called density matrix, and we can compute physical expectation value, just trace of this operator times this matrix law, and normalized trace law to be 1. So this is a description of expectation value. But if we rewrite in terms of wave function, just this is expectation value in terms of this ground state wave function. But in generic systems like open system, which some quantum system coupled to the other bigger quantum system, we often use this density matrix formalism, so that, for example, in finite temperature, we can just take this density matrix to be this canonical ensemble. And in that situation, we don't have this kind of identity. It's not just single eigenvalue, but it's a real Hermitian, real matrix. And then we have some, we call it such a state as a mixed state. But still, even for this mixed state, this definition of this entanglement entropy like this, it holds well. So there are no modification of that. But we have to be careful that in this case, in mixed state, then this kind of entropy is no longer measure not only entanglement, but also some classical contribution like thermodynamical entropy and so on. But still, we can define this as some nice quantity and call it entanglement entropy. So this entanglement entropy, especially for pure state, it measures this measure how much given quantum state is quantum mechanically entangled, as of course this word means, and how much complicated. But in other words, we can also look this quantity as some measure of some active degree of freedom or amount of information included in some system. For example, some ground state of some particular systems. And then also it is good to ask why this is interesting and useful. So this is often asked by many people, but can we observe this entanglement entropy in some real experiment? So far, this is very difficult, but maybe there are some nice breakthroughs, then we have very nice development, and indeed this is some developing subject, and there are several papers in that direction, but still there are no systematical understanding in this real experiment. But instead, actually, this plays a very important role to do some numerical experiment. So in numerical experiment means we have some very complicated Hamiltonian, and we compute its ground state, for example, energy or some ground state wave function. So that case, we did everything do it really computers, using computers and to somehow approximate the ground state. In this kind of calculation, somehow we notice that this entanglement entropy is easy to calculate. If we know some numerical way to describe ground state, then we can actually immediately compute this entanglement entropy, and this is quite nice observable in this numerical experiment to look at some basic property of ground state and so on. For example, this is one way to apply this to just compute central charges. So we have some very complicated Hamiltonian, and we cannot solve this model exactly at first sight, but still we can do numerical calculation. And if we compute entanglement entropy numerically, then we can estimate the value of central charge. So this is a very powerful method. Also recently, this kind of method is applied to detect some spin liquid, some so-called spin liquid space, which is really exotic state of matter. And also like this sphere such lectures yesterday, and also this is useful to detect Fermi surface even in strongly coupled systems. So this motivation of this entanglement entropy, especially from the viewpoint of condensed matter physics. So, so we define this entanglement entropy, but there is also some modification of this entropy, so-called Rényi entropy. And this, in the end, I'm going to use this quantity. So I just quickly mentioned that. So this is called Rényi entropy. And equivalently, this is related to the quantity called entanglement spectrum. So entanglement n is some positive integer, like 1, 2, 3, some integer. And nth Rényi entropy is defined by this quantity. Basically, it's a trace row A to some power n. And indeed, if we take n goes to 1 limit, this is obvious that we take n goes to 1, this is a derivative of about n, and it's just reduced to this entanglement entropy. So in this sense, this quantity can be regarded as some just generalization of entanglement entropy. And it includes more information than just studying entanglement entropy. So if we know all of this SAN, then if you know all of the trace row to some power, then we can recover all eigenvalues of this density matrix row A. So in this sense, this is called entanglement spectrum. Spectrum means eigenvalue spectrum of this reduced density matrix. Sorry, could you say? Okay. You mean of course? I mean, yeah. Of course, the entanglement entropy is parallel with this classical entropy. Channels. This also, I mean, parallel with just the eigenvalue of probability distributions classically. But I don't know the name of this classical analog of this. But it's just the eigenvalue of this reduced density, which is just probability distribution. Just probability itself exactly entanglement spectrum. So far, I'm talking about quite general aspects of this entanglement entropy. So now I'd like to move on to our more interest, which is quantum manifold systems or quantum field theory. So this entanglement entropy is now defined, can be defined in geometrical way. So this is the reason why sometimes people call this as geometric entropy. So there are lots of spins, electrons or spins like this. And we just pick a particular part of the spins, which we call A. And just actually, we can define this A as this kind of region, some space-like region in a spin systems. And just trace out the other part, which is called B. So this defines this kind of decomposition of Hilbert space. Total density matrix is HA times HB, like this way. And we trace out this HB. And if we take continuum limit to get some quantum field theory, then we have some time slice. This is time direction is orthogonal. We just fix some time. Then configuration of, for example, scalar field or fermion field on this space is exactly definition of this Hilbert space. So, sorry, yeah. No, anyway, we need to discretize this theory. Then we can factorize it. But there is some subtle issue about gauge field because there is a Gauss law concept. But except that, then it's direct to do this if we assume this kind of discretization. Yeah, of course. But anyway, we need to introduce cutoff, UV cutoff. Otherwise, this quantity is not well defined. I'll come back to that. But if once we can specify that, we can basically define this. So we define A and B, and we specify its boundary. So there are infinitely many different choices of this boundary. So, but once we specify this, we can have one quantity, which is SA. This is a definition of entanglement entropy in quantum field theory. So they are also, this is not directly related to this. So, yes? Conformal field theory. Yeah, but I mean, why you restrict to conformal field theory? We can just extend it to quantum field theories. Yeah. Basically, but anyway, we have to specify some way to discretize the system. But I should say, especially for gauge field, we have to be very careful about this separation because there is some gauge, Gauss law constant which constrains this configuration. So what happens for this links? In the lattice gauge theory, there are links description of gauge field link, not just point. So that means links penetrate, intersect with this surface. That treatment, that kind of bond, it's a bit subtle. But once you specify such a prescription, we can uniquely define this quantity. Any other question? Okay, so anyway, so this is a definition of this entanglement entropy in quantum field theory, and but especially maybe we are more focused on conformal field theory, which can be treated more simply. So also I'd like to mention some historical reasons why people got interested in this entropy. So it's interested rather not condensed matter, but really black hole physics. And it's quite long ago, like Tofuft and this Bomberi and collaborator and Sredoniki. At that time, we don't know how to describe black hole entropy by using string theory and so on. So this entanglement entropy is somehow smearing out sub-Hilbert space for B. So that means, roughly speaking, the entanglement entropy measures the lost information by this smearing process. Because the observer cannot see this region B, so somehow there is a lost information, and this is measured by this entanglement entropy. And this origin of entropy looks very similar to the black hole entropy. So black hole is surrounded by the event horizon, and the observer cannot see inside the horizon. And so maybe this is an interesting toy model of that. This is actually historical reason. And the boundary region of partial A is the event horizon, and so on. But actually, this kind of identification has some problem. And there are some partial answer to this relation, but there are some problem. But to really, we are interested, if we are really interested in the connection between entanglement entropy and some sort of gravitational entropy, we have to actually look at ADS-CFT correspondence, which is the latter half of my lecture. So anyway, so this is a famous Bekenstein-Hawking formula. Also, this is true for entanglement entropy. So anyway, entropy is written in terms of area of some surface. But if we keep this coefficient, physical coefficient, like the Boltzmann constant, must see the velocity of light, and Newton constant and h bar appears. And Boltzmann constant means that this should be closely related to this statistical mechanics, or more broadly, it's quantum information theory, some statistic information theory. And also, this Newton constant means, of course, this is closely related to gravity, because this is ordinary black hole entropy, some gravitational entropy. And h bar means this is, of course, quantum mechanical phenomena related to quantum memory systems. In this way, these three different subjects is very closely related with each other, especially through the idea of this quantum entanglement. And indeed, there are lots of recent active discussion about these relations. Okay, so the advantage of the use of entanglement entropy is like that. So this is already mentioned in some sense. So especially from the viewpoint of quantum memory systems, entanglement entropy can be used as a quantum order parameter. In a field theory language, we often use Wilson loops in gauge theory, but somehow more general, because we can define this quantity in any quantum memory system. So some analog of Wilson loops in more generic context. So this is useful to classify quantum phases, or detect some quantum phase transition. And also, this is a main aim of this main content of my my later talk. But this is the entanglement entropy offers us a very nice bridge connection between gravity and condensed matter systems. In gravity, of course, metric plays a very important role. And condensed matter system or quantum memory system, we need to know some ground state wave function. And once we know the ground state wave function, we can compute the entanglement entropy. On the other hand, in the gravitational picture, as we will explain, this actually gives area of some surface. So this and the area of surface and the holographic calculation of entanglement entropy says that this entropy is same as area, like previous formula of Bekenstein-Hawking formula and generalization of that. So that means this wave function is really connected to the background metric in this way. So this is quite useful to map between them. And finally, so maybe for statistical mechanical purpose, the understanding of non-equilibrium state is quite a hard problem. And one reason is that there are no thermodynamical equilibrium, as we cannot define nice quantity like entropy and so on. But still, we can always define this entanglement entropy in any quantum system, even if we have some non-trivial time evolution. So this quantity should be useful to understand some property of non-equilibrium systems, like thermalization procedure and so on. So these are some advantages. Okay, so now I finished this motivation of this entropy, and I go to the basic properties of this entanglement entropy. So I just give a few of some basic properties. And the first one is like this. So let's assume total system is a pure state. This total system is just a single wave function described by single wave function. And the total system is divided HA and HB like before. Then we can immediately show that SA is always same as SP. So we don't need to distinguish these two guys. This means that the entanglement entropy is not extensive. So if we increase the size of A, that means decreases the size of B because total size is fixed. Total. So, but still this equality is false, so their entropy is not proportional to the size of the subsystem A. The proof is immediate if we use this knowledge of this Schmidt decomposition. So Schmidt decomposition is like this. These are some also normal bases and some linear combination of this basis. This number of bases is always minimum of either of this Hilbert space dimension. So we can always have this decomposition. Then it is immediate to see this equivalence. And of course, by taking derivative n, we get entropy, which should be the same. So this is our first basic property. So SA equal to SB for pure state. And second one is more non-trivial. This is so-called strong subjectivity. So we assume total Hilbert space is A times B times C. And for any reduced any density matrix, we can allow even for this kind of even not mixed state. Mixed state is total mixed state is fine. And we can also even times something. We can tensor one more Hilbert space, still the result is same. And in this setup, A, B, C decomposition, and assuming that A and B and C don't have any overlap between them, then this inequality, these two inequalities is always true. Maybe I should write A plus B as some A union B. It's just a set, A and B is a set, and it's just A plus B means just union of the A union B. This sum and BC, and it's always greater than this combination. And the second one is like this. And actually, these two inequalities are equivalent. If we use the idea of this purification, actually these two guys are equal. So maybe you can just remember only one of that. But sometimes it's useful to write both of them. And from this, we can show this kind of inequality. This is like a triangle inequality. So A union B. In this case, actually, we assume A and B has an overlap as opposed to this condition. Just here, we have different rule. A and B has some overlap. In this case, we have this inequality. This is so-called subjectivity. And the other one is called Araki-Leap inequality. And it looks like a triangle inequality. This is, can be easy. This can be shown for any quantum systems which has some unitary property. Yeah, right. This one is the intersection. Is allowed. Yeah, sorry for this change. But anyway, this is equivalent, so we can just remember this inequality. Only that is enough.
Saturated.
That's a very good question, but yeah, there is some known result. But that is also written in recent paper in quantum pH. It's some bit long result. It's not so simply summarized result. So I cannot tell you immediately, but I can maybe if I can tell you some paper in that day. Sorry?
Physical picture, just to
Physical
see
picture.
change.
Maybe the holographic principle will give one basic picture, so I will come back to that. But yeah, maybe mathematically this is that picture. So strong subjectivity, just naively replace A and B is a very abstract set, right? But we can just change, regard A, B, C is just number. Then we have this inequality, and we can, particular case, we have this inequality. Choosing that this is the same, and this is x and y, this is x and y, and this is assuming the same, then it's x plus y over 2. And this is a familiar inequality, which means just this function is concave. Second derivative is negative. So this is a mathematical meaning of this inequality. But physical meaning, I'll come back later by using ADS-CFT.
Really sorry, I didn't understand that. Sorry. So the analysis that A plus B plus C is like X?
Yeah. X and big. Yeah. Okay, sorry. Let's see. X plus y is like this point. Yeah, so Sx, maybe I should. So we want to we want to find this point is at x plus y, and this point is 2x plus y, and this is bigger, so it's like. Yeah. Okay. So we can also define the quantity so-called mutual information, which is defined by this SA plus SB minus SA union B. This is a positive because of this subalternativity relation. This measures entropic correlation between region A and region B. And so this is, first of all, the strong subalternativity tells us that this is inequality. This is rather simple inequality. If we increase this one of the region, then entropy, but this mutual information actually increases some monotonicity property. And also another reason why this quantity plays a very important role is that actually it gives some bound for two-point functions. This is a definition of two-point function is actually tricky. We have to somehow smooth out because this is a local, naively in quantum physics, this is a local operator. It really has a lot of divergence, but we need to properly regulate it. Once we do that, so this is any operator, and we just talk about two-point function of any operator and subtract this trivial piece. Then this is always bounded by this mutual information. So mutual information gives maximum correlation of some two operators. So there are some such quantities known. Okay, so but I'm not going to this quantity in my lecture, so this is just some additional information for that. So next I come back to the more important property, so-called area law, found by these all the papers. So this is about the entanglement entropy in quantum field theories. And now originally this is analyzed in a free field theory, but now I update the result by using also ADS-CFT and many other results. And in general, entanglement entropy in quantum field theory includes UV divergence, ultraviolet divergence, because it's a really continuum limit of the theory, quantum mechanical system. So entropy is divergent, so we have to take into account some cutoff, UV cutoff. So this UV cutoff, we call it A. A is like lattice spacing, and in the end, we want to take A goes to 0. A goes to 0, it becomes continuum limit. And in that description, the leading divergence of entanglement entropy in my convention D plus one dimensional quantum field theory, we have one time and D space direction. That means it's ADS-CFT divided D plus two dimension, actually. But anyway, we have D plus one dimensional quantum field theory. But the important assumption is with a UV fixed point. That means that this is a sort of local quantum field theory. But of course, in particle physics, this is a quantum field theory which you normally work with, but not always in many model systems, somehow complicated systems. So anyway, under this assumption, this leading divergence is always proportional to the area of this boundary of subsystem A. This is a subsystem A, and the other part is with a B. And it's separation. This is sometimes called entangling surface. It's partial A. This boundary of A. We compute this area, and it's proportional to the entanglement entropy. But anyway, it's divergent. So its divergence looks like this. This is a dimensionless quantity. So area divided by A, the UV cutoff to D minus 1. So always, and with some numerical constant here. And this is the area law. And we have also, of course, there are lots of sub-leading divergence. And I will come back to this later, especially in holographic calculation. But anyway, leading piece is always like this. Intuitively, this can be understood like very simply. So we have some, this is we are talking about the entanglement, correlation between this region A and the other part. And the correlation, of course, should be most important near this separated point, right? This is partial A. Near the boundary, we have most strong correlation. So that should dominate the result. But of course, we have to be careful about especially careful about massless theory, then we have long-range interaction. But still, this result is true. Except 2 dimensions, that's what I come back later. So, but there are some comments on this. And this area law is, yeah, so I should also add one more thing. Sorry, this is this comment. So this, what we have in mind is this area law can be applied for ground state and finite temperature systems, finite temperature state, but not for a highly excited state. But of course, in particle physics, we normally look at the ground state, but in a real system, so maybe we try to excite the system by adding energy. If energy is finite, it's fine. Still, area law is still false. But if we highly excited system, like energy scale is like cutoff scale and so on, then this area law is violated. But the maximum variation, of course, volume law. So because log of dimensional Hilbert space is always proportional to volume, so maximum violation is low. We cannot exceed that. But in a highly excited system, we have volume law. Okay. Highly excited state is indeed this point and inside this region is highly entangled. Everywhere is entangled. Excited, really excited state.
So you said that the entanglement entropy diverges because of the correlation between near the edge. So in that sense, I mean, what is the extra information in entanglement entropy other than the say correlation among the? What do I suppose I know the correlation? So what do I get more out of the entanglement entropy?
But the correlation, yeah, I mean, entanglement entropy roughly means that it measures non-local correlation also, but it's a correlation in general. But if we particularly look at some scalar field coupled to fermion, you can also extract correlation between scalar field, right? That's a 2-point function of scalar field. So this is a more sophisticated information. But entanglement entropy just we sum everything at the same time. But it still also it measures some really non-local also correlation. Like we can think of 2 Wilson loops and correlation function of that. This is really non-local correlation between 2 extended regions. This kind of also captured by this entanglement. And not only this local 2-point function, but also non-local 2-point function.
Yes.
Yes.
In all these derivations, one of the assumptions that you made here is that the total Hilbert space can be written as a tensor product of individual Hilbert space. So when we have this strong correlations with this boundary, this assumption is, I mean, does it still hold?
I mean, sorry, you're talking about the separation in an A to B that might affect this.
So the total Hilbert space you're writing as so in this particular case, so if you have a Hilbert space, then you will be writing as a Hilbert space of A with cross some the complement of that set,
Yeah,
right?
Right.
So, but in case you have this strong correlations in your boundary with this with the set with this complement, so in that case, can you still write your Hilbert space as a tensor product with of 2 of them?
Yeah. I mean, anyway, we compute everything using some discretized picture. Then we can always think that at some point, one point where we have degree of freedom, and the other point there degree of freedom, and one point belongs to either of A and B. So this separation is exact. Is okay. And if we, for example, more precisely, so we have some separation. These are 2 points, and if we count number of such bonds, like it is exactly the same as this quantity area law. That it's bond this penetrates, bond intersect with this boundary of A. Its number of such a bond is exactly this number, and that gives this correlation. Okay. Any other question? Okay. So, yes. Sorry, ground state.
In ground state, entropy follow the area law.
Yeah.
But in excited state, entropy violates the area law.
In highly excited state.
Highly excited state. But in the case of the mixed state, sir.
The mixed state.
It is the superposition of the ground state and excited state. Area law will be violated or not?
mixed state.
In mixed states.
I mean,
Superpositions of the ground state and excited states.
and then if you mix ground state with highly excited state, it breaks.
But sir, here the ground state plus all the excited state, ground state, first excited, second excited.
Then it's violet. But this mixture, this weight, how we include this high excited state is like, for example, temperature, right? Effective temperature. If temperature is a cutoff scale, it's violet area. But if temperature is finite,
But sir, if we will take only the two states, the ground state and first excited state.
no. Then the first excited is no problem. Still this holds, area row holds.
And come some corrections.
Sorry?
The correction term will come in or not?
Prediction is of course there. Okay, that's correct. For example, if we talk about the first excited state, probably this part it changes. Exactly, that thing I'll come back to in the end of my lecture. Few days later.
Question? Sorry.
Yeah.
I mean, the area law you're showing here is like the entanglement entropy goes like the area of the boundary of that region. So and maybe in the next slide when you showed that the 1 plus 1 dimension, I want to know about the coefficient in front of that area over is that universal or?
Okay. This coefficient, right?
Yeah.
This is not because not universal in that sense this A is a cutoff scale and we can just change the cutoff scale. But only when we have this 1 plus 1 dimensional case, it is like logarithmic divergence. That case, this coefficient is universal, right? Doesn't depend on the naive renormalization cutoff scale. But in general, it's not universal. Yeah, so I should mention this 1 plus 1 dimensional case. It's like actually CF conformal field theory. It's like logarithmic behavior about dependence on this subsystem size L. It's log L divided by A because of dimensional reason. A is a cutoff scale. But in some sense, we don't have to call this exception because we can take D goes to one limit. Sometimes it becomes log. So it's sort of. But anyway, we have to be careful about 1 plus 1 dimension. And also the quantum field theory with Fermi size. This is heavily discussed by this severe such depth talk. So probably I don't go into so much details, but it looks like this. Like just we start with this 1 plus dimensional safety and multiply this factor L to L divided by A. Intuitively, this is because if we have a Fermi surface and we talk about the low energy excitation, it's like the orthogonal direction from this Fermi surface gives the main contribution like this. Right? So we have some Fermi surface, and this is the energy, and this is the momentum. This is the Fermi surface, and if we talk about low energy excitation, it's like linear dispersion relation along this radial direction. But we can forget about this orthogonal direction. So effectively 2 dimension. Like that's the reason we have log, and we have forget this ignore one direction. We have to sum over each dimension. So that gives this factor. But here we have to also mention that we take this cutoff scale to be Fermi surface energy. That means quite highly excited states. That's the reason we violate this area law. And if we just talk about the standard quantum field theory, and cutoff scale is very, very high, and the Fermi surface energy, Fermi energy is very small or finite, then this is not true. And it just result is like just area law plus some finite contribution which is given by this formula, but with this identification. Just we replace A with KF, and that just doesn't violate some area. Okay, so these are I explained this area law, but there is some. So if we can talk about this condition or this condition, so that if we don't assume local quantum field theory, or if we assume some highly excited state, then this is no longer true, and we have some volume law. And indeed, for example, if we forget about local condition and look at this very highly non-local Hamiltonian, this is a standard kinetic term for Hamiltonian in time direction, but we have exponentially large non-locality. Usually we have Laplacian here, del square, then the massless theory, but we exponential root Laplacian. Then it's very highly non-local case. This is my work with Shiba. Just a few months ago. And so this is, we plot this entanglement entropy computed numerically. So this L is a subsystem size. This 1 plus 1 dimension. So we just exactly same setup like this. And this L is like this distance. And then initially it's like a volume law like this. But if we take a L goes to very large, then because this term plays the role of some mass term, because this is it's infrared limit, so this is just goes to 0, and this is phi square. It goes to approach it to the constant. But if we look at A is very large, taking A goes to very large, then we get this kind of linear region, which is really volume law. So this is an example of volume law. And if we take generic non-local Hamiltonian, this is more generic result than area law. Okay, so also this proof of area law, rigorous proof is available, but mainly for free field theory, in my understanding. But in a strongly coupled theory or interactive theory, we can use ADS-CFT, which will also come back later. But still, this area law should indeed it's false. And also this UV divergence of area law, divergence is not good, but if we consider mutual information, and assuming this region A and region B is really separated, the divergence is cancels out automatically. We get some finite quantity. So sometimes it is useful to look at this mutual information. It's both, I think, both scalar and fermion. Any dimension, and any quadratic Hamiltonian, for example. At least this way.
You gave example of volume law for non-local quantum field theory, right?
Yes.
So is it true for any non-local quantum field theory, or just valid for the special example?
I think any. So if we have like a dispersion relation of this kind of shape, right? If dispersion relation is like very non-local, right? So energy is like exponential some k some power, then I think generically this is probably true. But of course, our analysis is just limited to free field theory because otherwise we cannot calculate everything.
Suppose I have a massless field and some other massive field. So suppose I integrate out the massless field. So I'll get some non-local field theory, right, in terms of massive field.
Yeah.
For that case also I'll get this.
If we assume this mass scale is, so A will take to be much smaller than mass scale, then highly non-local theory probably you get it. But it's a little bit subtle because if we choose, this is a non-local, exponentially some non-locality appears, but if we assume this del square some power, but if we have some, still this del square, not del square, but del some 8 or 10 or such power, and we think it's really not exactly local, but still result is area law in that case. So to get a non-local, to get a really volume law, actually this exponential non-locality is very important. There are some such issue about it, how much we define this non-locality. But once you get exponential non-locality, I think you have that. Okay. So I just done this. Okay, so so this area law is indeed it looks very similar to Beck-Einstein-Hawking formula, which is also again area law. But of course, they are different in that this Newton constant is finite in this Beck-Einstein-Hawking formula, but in our entanglement entropy is not finite, and that means they are not exactly the same. But there are one way to understand the connection, which is like quantum correction to the black hole entropy, especially the Susskind and collaborators working, and also some other group also working on that. But they are, roughly speaking, some, for example, loop correction to the Beck-Einstein-Hawking formula of entropy is actually regarded as the entanglement entropy. So we have some black hole and with some matter field, scalar field, and basically this entanglement entropy comes from this matter field, right? We have some region A, and the other part we trace out some part and we do some loop integral, and this correction from this scalar field or matter field can be identified with this black hole, some contribution to black hole entropy is identified with entanglement entropy. But of course, we want to understand this Beck-Einstein-Hawking formula itself, and for that, it is good to think of this ADS-CFT, which is my later lectures. Okay. So I also would like to mention again about this entanglement entropy in the context of some quantum variable systems. So the interpretation is like this. So this entanglement entropy is some effective rank of reduced density matrix. This is already clear from this expression. And this measures how much we can compress quantum information of some given quantum systems, and described by this law way. So if we think about some computer simulation of some quantum variable systems, we want to some compress impression so that we get efficient numerical calculations. But even if we try quite hard, but there are still something remains, something we have to really simulate. And this amount of minimum amount of calculation which is required is actually measured by this entanglement entropy. So this may estimate the difficulty of these realist computer simulations, such as especially in the DMRG, or there are many powerful methods. And in that context, actually, I say people notice this importance of this quantity. And more physical sense, in other words, we know that such a simulation computer calculation is quite hard at the critical point, quantum phase transition point. Indeed, entanglement entropy gets divergent at this quantum critical point, and that means we can use this quantity as a quantum order parameter.
Sorry, Tadashi. I myself don't understand this very well. So if at the quantum critical point you have a conformal field theory, one of course has this area law divergence, but is there an extra divergence?
I'm talking about area law divergence, actually. So if we consider some spin system, some infinite spin chain, it's like for gapped system, like X is a correlation length, and A is cutoff scale, and this is actually finite. But if we go to the critical point, this enhances into this way.
I see.
And if we take A very large, this is really
I see.
big.
Thank you.
Yeah, indeed, that's exactly what I wanted to explain here. So if we plot this entanglement entropy, we just somehow spin chain, Ising spin chain with the transverse magnetic fields, this Ising model in Z direction, and the X direction we have magnetic fields. And we have some of this entropy and versus some coupling constant lambda. If we go to large lambda, actually we can forget about this magnetic fields. So that's just standard ferromagnetic phase of this Ising model. That actually gives log 2 because of up-down degeneracy. But in a small lambda, we have very large effect by this magnetic fields. So that breaks this ferromagnetism phase. So we have paramagnetic phase, and it's opposite different phase. There are phase transition between them, which actually lambda equal 1, and there this entanglement entropy diverges. So it's like this, like here, like this, and this cushy actually correlation length is divergent at the critical point. So it's like this, and it actually cross over this formula, like this. So in this sense, it's clear that this can be useful as quantum order parameter. But of course, still in this case, still this is a dynamical system. We can use some other operator as a order parameter. But in some cases, there are some cases where we can only have to use some topological quantity like this entanglement entropy. So, for example, some mass gap theory with some topological phase. So entanglement entropy behaves like this. This is the area of divergence here, L over A. 2 plus 1 dimension is linear, and some plus constant. And this constant part is so-called topological entanglement entropy. And this is really topologically invariant quantity. That means even if we change this choice of subsystem a little bit, some smooth deformation of subsystem, still this finite piece doesn't change. So this gives a quite nice topological property, and that gives some very important information. So this gives some order parameter of topological systems, and we cannot detect such a thing by looking at just local correlation functions. It's quite non-local correlation. This is it's something like degeneracy in complicated topology. If we have some quantum field theory, topological field theory on a very complicated geometry like higher genus or something like such a surface, there are some particular degeneracy appears. This kind of degeneracy roughly detects this quantity. Or maybe degree of freedom of any, for example, you can think of degree of freedom of anyons, right? There are some non-local constituents. That kind of number can be estimated by this quantity. So it's anyway, this is entropy, right? So degree of freedom. So this counts the number of degree of freedom of such a topological object. That gives some. Sorry, these are so-called quantum dimension. But it's not exactly standard dimension. It's some defined in a bit abstract way by looking at some. There are non-local objects and they have non-trivial OPEs, like we are in the algebra. It's like non-local, non-abelian. During that, we can talk about degeneracy about such non-abelian object and define that way. Sorry, I didn't have time to explain it. So also, yeah, we can pick up this quantity by taking this combination. And this combination is good because we can forget about this divergence. It cancels as divergence. And we can pick up this concept. This is a heavily used formula in these topological calculations. But anyway. Okay, so now I'd like to explain the calculation of this entropy in quantum field theory. Go back to this mailing route. And there we heavily use the idea of so-called replica method. But basically, this says that this formula is very simple, just SA equal to rho log rho. But now just represent this as a derivative about n, like Rényi entropy. If we take n derivative of n, we have log rho, and we get rho log rho, like this formula. And we can also rewrite this in terms of log of Torres, because Torres law is normalized. Torres law A is always normalized to be 1, so this is equivalent. So into this CFT, so we can just, calculation itself we can generalize in higher dimension, but explicit result can be only obtained in 2D CFT essentially. So we just, and also about for this our presentation, it is useful to concentrate on 2D CFT, so we just concentrate on that. And this replica method is very powerful in this case. And the idea is just to use path integral formalism. So we have some wave function, Brown and Ket, and it's defined from path integral in Euclidean, this is a Euclidean time, from minus infinity to some time, and we just take this to be 0, t equals 0. Because of this path integral, everything is really projected down to ground state. This is a ground state wave function of quantum field theory. And so if we specify this some functional shape of this scalar field or Fermi field on here, exactly here, then that gives argument of this vector. And the opposite is also true. So now we express this rho A, reduced density matrix. We have to trace out region B. So that means we just paste with each other these previous two copies and paste with each other here. And still region A is open. So boundary condition of A in the upward and downward is that keep open, and we just call it AB. This is the argument index of density matrix rho A. So now we finally compute trace rho A to some nth power. So we just take matrix multiplication in the times and trace, in the end we contract index. Contract index means just we paste with each other. Like before, we paste this lower cut and upper cut, and successively we do that, and in the end finally connect this guy to this. And in the end, what we get some compact, some without boundary, some manifold without boundary, because this cut is now pasted with each other. So in the end, we get this kind of n-seated Riemann surface. We just call it sigma n. And the partition, this trace law to the n is just equivalent to partition function on this little bit complicated manifold. So path integral over this n-seated Riemann surface. So in this way, we obtain the following representation. So trace law n is actually Zn. Zn is actually partition function on Riemann surface sigma n. But actually, to be honest, we have to divide by some normalization factor Z1, so that we want to realize this condition. If we set equal n1, this should be 0. So this is just normalization condition, and which also appears everywhere. So here we talk about partition function on this manifold, but divided by this total partition function Z1. So there is some n copy of this, and then we get this factor. So And so anyway, up to this point, we can just easily extend this analysis in higher dimension. Any dimension we can use. But from now, we focus on two-dimensional field theory so that we explicitly evaluate this formula. So to evaluate this, we would like to first consider the case where the CFT is just simply defined by free scalar field, complex free scalar field, because this is a pedagogical example. And it's complex. Real scalar has a central charge 1, but there are 2 because it's complex, so it's C equal 2. And then in this case, it is actually useful to introduce n replica fields on complex plane, such that we have this kind of configuration. So we have n seeds, and in n seed geometry, we have a single scalar field. But now we rewrite this theory equivalently in terms of just single seed, but there are n scalar fields, phi 1, phi 2, phi n, like this way, on just single complex plane. But with non-trivial boundary condition, right? Because if we go to the another seed, we have a different index. So phi k means actually scalar field on k seed. So it's phi k goes to chi k plus 1 if we want to go to this one across this cut, and the opposite thing is also true here. So we have this twisted boundary condition. But to make more, simpler description, we can do some discrete Fourier transformation like this, and we define diagonalized shape, diagonalized boundary condition we get. It's just exponential to pi I k divided by n because of this phase factor. So this is rather familiar boundary condition, which is typical in Obifol's theory. And indeed, we can use the language of Obifol's theory and some results there. And so these are twisted boundary condition. But anyway, we are looking at the ground state. So we have to think about the ground state of twisted sector. And such a ground state of twisted sector is generated by some lowest dimensional twisted boundary, twisted vertex operator, which we call sigma k over n. So we just start with some vacuum. There are no twisted boundary condition, but we multiply this lowest dimensional twisted operator, which is called sigma k over n. Then we have some non-trivially twisted boundary condition. So this is a twisted boundary condition, sigma k over n, and it's like, because we have n seeds and there are n different kind of fields, so that means we have n copies of 2-point functions. And just 2-point function is completely fixed by conformal dimension of this operator. This can be computable. This is, for example, a very simple exercise which can just compute zero energy contribution in twisted boundary condition, like Polchinski's textbook. And if we do that, we get this result, conformal dimension for a k sector, and we have to sum over each k, and then we get this factor, just sum of this. And then in the end, so we find this formula. So this is a reason because we, as I explained, so we choose the C is just 2 for this complex scalar field. Just we rewrite this 1/3. It's like a C over 6. But this is the formula actually true even for general 2D conformal field series. But simply the reason is that it's a 2-point function. It's like a 2-point function is quite universally computable. But I will come back to more detailed proof later. But anyway, so if we have this formula, we just take derivative about n. Right? We have a factor 2 come here, and then we C over 3 and log L divided by A. L is a distance between these 2 points. 2 points means these 2 points. And this is exactly the size of subsystem A. Size of subsystem A is L, small l. And for dimensional reason, we have to divide something, and we just put this UV cutoff. Because we expect that when L is cutoff scale, everything is gone because there are no degree of freedom. That means entropy should vanish. So we impose L equal A is 0, and we get this formula. This is a famous formula first found by Holzen, Larsen, Wilson, and this is the explicit result for 2D CFT. But if we are interested in more detailed proof of this, except this more than free field theory, we can use the proof which found first by this collaborator Cady 10 years ago. And there we can just use a formal argument looking at conformal map. We can particularly choose this conformal map. And we have n-seated Riemann surface, exactly what we discussed just before. And this is just simply mapped to just single seed. because of this factor n. It's removed this multiple cut here. And then we can compute this energy stress tensor transformation. So energy stress tensor here, from here to here. There is some, of course, there's a conformal dimension 2, so it's like this. But there are anomaly term, which is very famous, which is proportional to the Schwarzian derivative term. And this gives additional constant contribution. And we can regard this contribution as some conformal dimension of this operator inserted here. If we have some primary operator inserted U and B, then we have exactly this contribution. So from that, we can read off this conformal dimension of these primary operators inserted here, actually twisted vertex operator, and given by this. And in the end, we have n seat, we multiply n, and we get this result. And indeed, this exactly reproduce this result. Exactly this result we get. Yes? Okay, yeah. Anyway, so we didn't discuss the normalization of here. Right? Actually, this normalization depends on cutoff scale A. Because of dimensional reason, we should choose this way. Because I mean, this correlation should be dimensionless, then we have to put this way. Okay. But the detailed constant, right, is not so much clear. So there's some ambiguity, actually, additional piece because of that. Any other questions? So, okay, so just, so this is a summary of this result. I didn't explain this, but there are some other variations of this kind of calculation by using exactly similar conformal map, and we can compute this. For example, circle case, it's like the sine function appears because of periodicity. If you have boundary, we have additional piece called boundary entropy, G function. And it's a final temperature, we have sinh, is some analytical continuation of this circle formula. And if we have mass gap, we have this formula, Xi instead of x. We replace just x with Xi. And if we have some finite, size system, the result is complicated at finite temperature. We have some finite size, compactified space, and with some final temperature, then we have some torus geometry, and we have to twist operator on torus. And we can do it exactly for free fermions, but the result looks a bit complicated. It's like log of theta function and plus some additional piece. But this additional piece is very important to explain this thermodynamical entropy. And yeah, maybe do you think it's good to stop here, or? Just a few minutes is fine. It's a few minutes, just finished. I just finished with this one. And this is the final thing I want to mention is an entropic proof of C-theorem. And this is a two-dimensional C-theorem, but recently also three-dimensional F-theorem has been proven by similar method, but it's more complicated, so I don't want to explain here. But 2D, it's very simple. So we just use strong subjectivity. So we consider some relativistic quantum field theory, and this is time and space. And we choose subsystem A and B, and use this strong subjectivity. So in this formula, sorry, we assume A and B have some overlap. Its previous formula, we call it AB and BC and ABC and B here, but it's equivalent. And we choose AB in this way, so slightly tilted, boosted shape. Because this is a Lorentz invariant, we can just, this result for A, entropy for A is actually equivalent to its boosted, this constant time slice result. So we just boosted A and B, then we can easily identify A union B. This is a Hilbert space A plus B is always here, and a overlap of A between A and B is always here, because some signal which reaches A and B always have to pass through this region. And then, so we have this strong subjectivity, and now we notice that geometrically we notice that length of invariant length, Lorentz invariant length here, A and B, its multiplication is equal to the length A union B times A overlap and A union B. They are same. And we take some exponential of that log of this. Log of A is called A and B. And then we as we already explained, we have some this kind of inequality, like this concave nature. And this means second derivative of S is actually negative. And indeed, this formula, previous formula says that this will have three, at a fixed point we have this. And that means, X is actually, this one is X, essentially X. Log L is defined to be X. So second derivative means that in this case it's actually, first derivative of SA equals central charge. So that, and second derivative negative means that this is a monotonically decreasing function about length direction. So if we increase the length scale, X direction, then this effective central charge decreases. So this is some proof of C-theorem. This is first formed by this Cassini and Well. That is independent from, totally independent method from the more famous, more traditional way to prove C-theorem. Yeah, okay, so I just want to finish here. And the higher dimension is quite difficult, and we have to use holographic analysis. Thank you very much.
Questions? Questions?
When you argue entropic C-theorem, did you use the unitarity?
Yeah, because the strong subjectivity only true for unitary theory.
Ah, I see.
Using positivity of Hilbert space.
Thank you.
So the entanglement entropy is proportional to the central charge only in 2D CFT. So what do we expect when we have some higher dimensional CFT?
Higher dimensional CFT.
Yes.
That's a good question. And in higher dimension, for example, especially in even dimensional conformal theory, central charge only defined in even dimensional conformal theory. In that case, coefficient of logarithmic term always related to central charge. But details is a bit complicated because in 4 dimensions there are 2 central charges A and C, and higher dimension more. It's in general coefficient of logarithmic divergent piece of entanglement entropy is a linear combination of these central charges. And the coefficient of this linear combination depends on how you choose this details structure of this subsystem A.
So can one still apply the replica trick that you mentioned?
Sorry.
So can one then apply the replica trick that you mentioned to compute the higher dimensional CFT, entanglement entropy of higher dimensional CFT?
Higher dimensional CFT? Sorry, maybe I'm not completely sure, but maybe we can just look at the 4-dimensional case. Sorry, this is the I just give some express example. So in 4D CFT, we have area of divergence, which looks like a square, L over A square. But the coefficient we don't know. It's not universal, as already also in some discussion. But this logarithmic term, log L over A, is some related to central charge. And especially if you choose round sphere with length L, its region A is like S2. The boundary of subsystem A is so that it is S2 with length L. Then it's like 4 times A CFT. This A is cut off, but this A is central charge of CFT. One central charge is called A, and it's like some constant. This is some generally true in CFT, and we can naively extend similar formula also true for more higher dimensional, even dimensional CFT.
Tadashi, what would happen if it's not the round sphere? If
Now,
it's
round
more,
sphere, you get another central charge C.
I see.
Also appears some.
So it depends on the shape of
Exactly.
I see.
So can one compute entanglement entropy for some arbitrary shape of
Object shape. That's technically quite hard. But for example, if you look at this holographic approach, at least you can just calculation just to find some minimum surface, which is clearly classical. To need to solve classical and partial differential equation. And if you can do at least numerically, then you get some result. But in general, it's quite good. I mean, analytical result is quite
Even for
difficult.
free theories, one cannot.
Free
Even for free theories, one
yes,
cannot.
it's still complicated actually. I don't know how to get the analytical result for that.
Any other question?
The entropy theorem proof here from is for only
Why don't you say that?
Entropy.
that entropy C-theorem proof we are from
Yes.
the last slide. So it is only for 2 dimension, right?
Yeah.
So can it be extended to higher dimension?
Higher dimension. Oh, I see. I mean, in 3 dimension, the analog central charge for F function recently introduced by Puri property. The odd dimension. There is a F, and 3 dimensional F theorem has been proven by looking at strong relativity, the same order, Cassini filter. But if you talk about 4 dimension or higher dimension, we don't know. The main difficulty comes from that in 2D, it's very simple. We just have single, just interval, right? It's just only topology for interval. And we just combine 2 intervals to show this kind of analysis. But if we go to higher dimension, we have to talk about some sphere and sphere. But the intersection of sphere is more complicated geometry. So it's quite difficult to handle. And also there are lots of source of divergence. If we have some inequality, but if we have divergence, it's trivially satisfied. We cannot easily extract some trivial. So it's technically, at least technically, it's quite hard. Nobody succeeds. But maybe just.
Yeah, there is a question.
Yes.
Maybe you already explained, you already mentioned that. So reduced density matrix is very similar to the density matrix in thermal density matrix in canonical ensemble. Are they same or different? Thermal density matrix and.
Yeah. So I mean, what I'm saying is rho A is usually defined from this canonical ensemble.
Yeah,
They don't agree.
I mean, you define some reduced density matrix in quantum entanglement